In this video, we're going to look at the birthday paradox, though it is not actually a paradox. So here's the setup for the problem. Instead of considering people and birthdays, we are going to consider balls and bins. So we have in bins, K balls, and we imagine the balls being uniformly distributed at random into the bins. The birthday paradox is specifically concerned with how many balls K until the probability of a pair of balls occurring in the same bin is greater than 1/2. So we're looking for the K value. So in the birthday situation, in is 365. The bins represent days of the year, and the balls are people, and we imagine people being randomly assigned to days of the year. And so we want to know how many people, how many balls until a pairing occurs where two balls end up randomly in the same bin. So the reason this problem is probably well known, and a lot of the standard probability problems that we're looking at in these videos are well known, is because they have surprisingly easy analyses. And it seems like the reason the analyses are easy is because the event we're looking at has a complement that's very easy to count. So the event that a pair exists is the logical complement to, so I guess we'll denote logical complementation with this notation, as a logical complement to the event that all balls in separate so the event that at least one pair exists is the logical opposite, that all the balls are in separate bins. And this event is easy to count, and so we have the probability of E1 is equal to 1 minus the probability of E2. So let's look at this E2, the probability that all balls in the first K balls are in separate bins. So there's a number of ways to express that probability or to analyze it. The first way is Pierre counting. So we can think of the sequence of balls and assigning them to bins is assigning labels, the bin labels, to each ball randomly. This should be in random order. So how many ways are there to assign in bin labels to K balls? Into the K, right? So there's into the K possible sequences when we have K balls, and we want to figure out the fraction of those sequences where all the balls remain in separate bins. Well, if all the balls remain in separate bins, that means we are selecting in, or rather we're selecting K of the in balls. We're selecting K of the in bins, which will be the bins that have balls in them. And there are K factorial orders for this to happen. So this expression counts E2. And so the probability that at least one pair exists is simply given by so for the specific birthday problem, n would equal 365, and then we simply have to solve for K such that this entire expression is greater than or equal to 1/2. Now, a problem with the Pierre counting approach is that this expression can be computationally unwieldy to deal with. particularly counting factorials for large numbers, is not a thing that computers necessarily like to do. So we'll do one more analysis using explicitly using probabilities. So this analysis is based on the fact that the following conditional probability is easy to express. So the probability that the kth ball winds up in a empty bin, given all prior balls have ended up in empty bins, is n minus k minus 1 over n. Right, so there's n bins. These k minus 1 balls are all separate, meaning there remains only n minus k minus 1 empty bins remaining. So the probability that the kth ball ends up in an empty bin is given by this expression. So because of that analysis, we can build up a full expression for the probability that all the balls are distinct. So the probability that the first ball is distinct is 1. Probability that 1 and 2 are distinct is given by this expression. And note, we already know the form of this expression. It's equivalent to this. So since k in this case is 2, n minus 1 over n, and then the probability of p1 we already computed. And so this pattern can be iterated all the way up to k. So to do one more, so for the third ball, again, note we know how to compute this. Here, k is 3. So we're going to have n minus 2 over 1. And then we just computed probability of 1 and 2, which is this. So the general pattern of all balls remaining distinct up to k balls is given by this expression where we distribute out the minus sign for the last term. And so we're going to bound this expression. For the last segment in this video, we're going to bound this expression because remember, again, the probability that at least one pair exists, which is the probability we are interested in, is equal to 1 minus the probability that all balls are distinct. So we want to bound this expression, which we found an expression for over here, in order to find a bound on the probability that we're interested in. So we're going to take the expression we previously derived. We're going to do a simple algebraic manipulation. So now we're going to derive a bound for these terms from the Taylor series for the exponential function. So the first two terms of the Taylor series of the exponential function are 1 plus x, which you'll note is what these terms are, the same form as these terms. So e to the x is greater than this expression. So we're going to find an upper bound for this term in the form of the exponential expression. So we'll have e1 minus n, e minus k plus 1 over n. So this is equivalent to, we're going to factor out a negative 1 over n, and then we simply have the sum of the first k plus 1 terms. So this is our final upper bound for the probability that all of the balls remain in distinct bins. So again, for the birthday problem, we would set n to 365, and then we would solve for k such that basically such that this value is less than 1/2. Because when this value is less than 1/2, the probability that we are interested in is greater than 1/2.